Hey guys, tonight we are going to drift through the largest mystery the cosmos has ever offered us. Settle in wherever you are, however you are. Let your shoulders drop away from your ears. Unclench your jaw just a little. Let the weight of whatever you have been carrying today slide off you, even just for a while. You do not need to hold onto anything right now. The universe will keep spinning whether you watch it or not. That is the first thing I want you to feel tonight. The permission to let go. Because what we are going to talk about is precisely about letting go. Not yours, the universe's. You are lying down or sitting back. And somewhere beneath you, the Earth is doing exactly the same thing it has done for billions of years, turning slowly, almost lazily, carrying you through the dark without any effort on your part. You can feel the stillness of the room around you, or perhaps the gentle hum of something mechanical, a fan or an air conditioner. Something steady and predictable that tells your nervous system it is safe to rest. And if there is no sound at all, that is even better, because silence is just another texture in the fabric of tonight. And silence is what we need to hear the quietest story ever told. The quietest story is the story of dark energy. It is a story about something so vast and so invisible that most of us will go our entire lives without ever thinking about it. And yet, it makes up the majority of everything that exists. You breathe in, and the air you pull into your lungs is made of atoms, ordinary atoms, carbon and nitrogen and oxygen, the same stuff that makes up the stars and the planets and the skin on your hands. And those atoms, as wonderful as they are, as necessary as they are, account for barely 5% of the universe. Think about that for a moment. The entire world you know, every person you have ever met, every mountain and ocean and forest and city, every book you have read, and every song you have heard, and every memory you carry. All of it is constructed from 5% of what is out there. The rest is something else entirely. Something dark. Something we can barely describe. So tonight, we are going to talk about the other 95%. We are going to talk about the part of the universe that does not glow, that does not reflect light, that does not interact with the senses you use to navigate your daily life. We are going to talk about dark matter briefly, because it plays a supporting role in this story. And then we are going to settle into the main character, the one who has been pulling the strings from behind the curtain for nearly 14 billion years. Dark energy, the force that is slowly, patiently, almost tenderly pushing everything apart. You can picture the universe as a vast dark room, not a scary room, not an empty room, but a room filled with soft things you cannot quite see. There are islands of light scattered throughout, clusters of galaxies, each one containing hundreds of billions of stars. And between those islands, there is space, an enormous amount of space, far more than you can comfortably imagine. And in that space, something is happening. Something very slow and very steady. The islands are drifting away from each other, not racing, not fleeing, just drifting, the way two boats on a very large lake might drift apart when the current between them is gentle and persistent. That drifting is what dark energy does. It is not a force in the way you usually think of forces. It does not push or pull in the conventional sense. It is more like a property of space itself, a tendency for space to expand, to stretch, to create more of itself between the things that already exist, and the longer it goes on, the faster it goes. That is the part that surprises people. The expansion is not slowing down. It is accelerating. And that discovery, that single impossible finding, changed everything we thought we knew about the cosmos. But we are getting ahead of ourselves. Let us slow down. Let us take this one step at a time, the way you would take a walk through a quiet neighborhood in the very early morning, when the light is still soft and blue, and there is no one else around. We are going to walk through the history of this idea. From the first time someone wondered whether the universe was expanding at all, to the moment when two teams of astronomers looked up at the sky and realized that the expansion was speeding up, to the strange and beautiful theories that have emerged to explain what might be causing it. Before we get to any of that, though, let us talk about what the universe is actually made of. This is the part where the numbers start to feel almost comical in their imbalance. Imagine you are looking at a pie, a very large pie. You are going to divide it into 3 slices. The first slice, the one you can actually taste and enjoy, the one with the visible filling and the flaky crust, that is normal matter. It is 5% of the pie. 5%. Everything you have ever seen, touched, smelled, heard, or tasted. Every object ever manufactured. Every living creature that has ever existed. Every drop of water and every grain of sand. All of it together makes up 5% of the total content of the universe. The second slice is larger. It is about 27% of the pie. This is dark matter. You cannot see it. You cannot touch it. It does not interact with light or any form of electromagnetic radiation. It is completely invisible to every instrument we have built, every telescope we have pointed at the sky. And yet, we know it is there. We know it is there because of its gravity. Galaxies spin in ways that do not make sense unless there is extra mass holding them together, mass that we cannot see. Clusters of galaxies are bound together by gravity that is far too strong to be explained by the visible matter alone. Dark matter is the invisible scaffolding of the cosmos, the silent structure that allows galaxies to form and persist. It is like the bones inside your body. You cannot see them from the outside, but without them, everything would collapse. And then there is the third slice, the largest slice, 68% of the pie. This is dark energy. It is not matter at all, not in any traditional sense. It does not clump or gather. It does not form structures. It is spread evenly throughout the entire universe, a kind of background pressure. a property of empty space itself that causes space to expand. If dark matter is the scaffolding, dark energy is the thing that is slowly pushing that scaffolding outward, stretching it, making the universe larger and larger with every passing second. Think about those proportions again. 68%. More than 2/3 of everything that exists is this mysterious pressure that we can only detect indirectly by measuring how fast galaxies are moving away from each other. We do not know what it is. We have theories, as we will discuss, but we do not know. We are living in a universe whose majority composition is an open question. That is either the most humbling thing you have ever heard or the most exciting, depending on how you choose to look at it. For tonight, I would like you to look at it the way I do, which is as a kind of cosmic lullaby. The universe is mostly mystery, and that is okay. That is more than okay. It is beautiful. You are breathing slowly now, in and out, and with each breath you are participating in the same atomic processes that power the stars. The carbon in your cells was forged in the hearts of ancient stars that lived and died billions of years before the Earth existed. You are made of star stuff, as the saying goes, and that star stuff is 5% of the cosmos. The other 95% is something else, something that does not glow and does not clump and does not form the kinds of structures we recognize. And yet it is there, filling every corner of space, every gap between every galaxy, every void that stretches for millions of light years. It is everywhere, and it is doing something. It is pushing. To understand what it is pushing and why that matters, we need to go back. We need to go back to the early 20th century, to a man who was sitting in a patent office in Bern, Switzerland, thinking about light and time and space. Albert Einstein. You know the name, of course. Everyone knows the name, but what you may not know is that when Einstein published his general theory of relativity in 1915, he was not thinking about the expansion of the universe at all. He was thinking about gravity. He was trying to understand how mass and energy curve the fabric of space-time, how planets orbit stars, and how light bends around massive objects. His equations were brilliant, elegant, and they made a prediction that Einstein himself did not want to accept. The prediction was that the universe could not be static. According to his equations, the universe should either be expanding or contracting. It could not just sit there, unchanged, the way most people at the time assumed it did. The prevailing view in the early 20th century was that the universe was eternal and unchanging. Stars might be born and die, but the overall structure of the cosmos was fixed. The galaxies were where they were, and they would stay there forever. Einstein did not like what his equations were telling him. He liked the idea of a static universe, and so he did what any good theoretical physicist might do when faced with an inconvenient result. He added a term to his equations. That term was the cosmological constant. It was a number, a a single adjustable parameter that Einstein introduced to counteract the tendency of his equations to predict expansion. Think of it like a dial. The natural tendency of the equations was for the universe to move, to change, to grow or shrink. Einstein turned the dial to a setting that would hold everything in place, a kind of mathematical counterweight that kept the universe static. He called it the cosmological constant, and he believed it was necessary to make his theory match the observations of the time. And then, about a decade later, observations changed everything. An astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, pointed a large telescope at distant galaxies and noticed something remarkable. The light from those galaxies was shifted toward the red end of the spectrum. This redshift meant that the galaxies were moving away from us, and not just a few of them, all of them. The further away a galaxy was, the faster it was receding. The universe was expanding. Einstein was devastated, or at least that is how the story goes. He reportedly called the cosmological constant the biggest blunder of his life. He had added this extra term to his equations to keep the universe static. And then the universe turned out not to be static at all. It was growing, stretching, carrying galaxies away from each other like leaves on the surface of an inflating balloon. The cosmological constant was unnecessary, or so it seemed. For decades after that, the cosmological constant was largely abandoned. It became a cautionary tale, a reminder of what happens when a scientist lets their preconceptions override the math. Physicists preferred models of the universe that did not include it. The universe was expanding, and the question was not whether it was expanding, but how fast, and whether that expansion would eventually slow down, stop, or reverse. The leading view was that gravity, the mutual attraction of all the matter in the universe, would eventually win. The expansion would slow. The galaxies would continue to drift apart, but more and more slowly, until eventually the process halted and the universe began to contract. A big crunch, everything collapsing back into a single point. That was the story for most of the 20th century. The universe was expanding, but slowing down. The question was how much matter there was, because the amount of matter determined the geometry of the universe and its ultimate fate. If there was enough matter, gravity would eventually pull everything back together. If there was not enough, the expansion would continue forever, slowing but never stopping. And if there was exactly the right amount, a precise balance, the expansion would slow to a halt at infinity. Scientists spent decades trying to measure this. They built bigger telescopes, developed better instruments, and tried to weigh the universe. They counted galaxies, estimated the mass of galaxy clusters, and tried to determine the density of matter in the cosmos. And the results were frustratingly ambiguous. It seemed as though there was not enough matter to halt the expansion, but the measurements were not precise enough to be certain. The universe seemed to be in a state of open-ended expansion, drifting outward forever. But no one could say for sure. And then came 1998. 1998 was the year everything changed. Two separate teams of astronomers, working independently of each other, reached the same impossible conclusion. The expansion of the universe was not slowing down. It was speeding up. Let me tell you how they did it, because the method is beautiful in its simplicity and its patience. These teams were studying a particular type of exploding star called a type Ia Supernova. You do not need to know all the details of stellar physics to appreciate what these objects do. But here is the essential point. Type Ia Supernovae are what astronomers call standard candles. They are explosions that always release roughly the same amount of light. When a white dwarf star, the dense remnant of a sun-like star, accumulates enough material from a companion star, it reaches a critical mass and explodes in a thermonuclear detonation that is remarkably consistent in its brightness every time. Every single type Ia supernova shines with approximately the same intrinsic luminosity. This consistency is extraordinarily useful. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it is. It is the same principle you use when you see a candle in the distance. You know roughly how bright a candle is, so if it looks dim, you know it is far away. The supernovae are the same idea, just on a cosmic scale. They are candles so bright that they can be seen across billions of light years. And because they are standard candles, their apparent brightness tells you their distance with remarkable precision. The two teams were the Supernova Cosmology Project, led by Saul Perlmutter at the Lawrence Berkeley National Laboratory, and the Heisey Supernova Search Team, led by Brian Schmidt and including Adam Rees. Both teams were doing essentially the same thing. They were searching for type Ia supernovae in distant galaxies, measuring their brightness, and using those measurements to determine how fast the universe was expanding at different points in its history. Here is why that works. Light takes time to travel. When you look at a distant object, you are seeing it as it was in the past. A galaxy that is 1 billion light years away is seen as it existed 1 billion years ago by looking at supernovae at different distances. The teams were effectively looking at different epochs in cosmic history. Nearby supernovae showed them the expansion rate of the more recent universe. Distant supernovae showed them the expansion rate of the ancient universe. What they expected to find was that the expansion rate had been faster in the past and slower now. Gravity, after all, pulls things together over billions of years. The mutual attraction of all the matter in the universe should have been slowing the expansion. The distant supernovae, representing the younger universe, should have shown a faster expansion rate. The nearby supernovae, representing the more recent universe, should have shown a slower one. That is not what they found. What they found was the opposite. The distant supernovae were dimmer than expected. Dimmer meant further away than the standard models predicted, and the only way they could be further away was if the expansion of the universe had been slower in the past and faster now. The expansion was accelerating. Think about how strange that is. Imagine you are watching a ball that you have thrown upward into the air. You expect it to slow down as gravity pulls it back toward the earth. That is what gravity does. It attracts. It slows things down. But what if you threw the ball upward, and instead of slowing down, it sped up, accelerating away from you, faster and faster, defying everything you know about how gravity works? That is what these two teams found when they looked at the universe. The cosmic expansion was not slowing. It was speeding up. The two teams announced their results within weeks of each other in 1998. The scientific community was stunned. This was not a small adjustment to existing models. This was a fundamental revision of our understanding of the cosmos. Something was causing the expansion to accelerate, something that acted in opposition to gravity, pushing galaxies apart with a gentle but relentless pressure. And that something was given a name that harkened back to Einstein's abandoned idea. Dark energy, the cosmological constant, the term Einstein had introduced to keep the universe static, and then discarded as his greatest blunder, was suddenly back on the table because a cosmological constant, a constant energy density filling space uniformly, would do exactly what the observations suggested. It would cause the expansion of the universe to accelerate. It would act as a kind of anti-gravity, not by repelling matter, but by stretching the space between objects. Einstein's biggest blunder had turned out to be right, or at least the mathematical form of it had. The cosmological constant was not there to keep the universe static, as Einstein had intended. Instead, it was the thing driving the acceleration of the expansion. The dial Einstein had turned was real. It just did not do what he thought it would. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the Nobel Prize in Physics in 2011 for this discovery. It was one of the most significant findings in the history of cosmology, and it fundamentally altered the way we think about the universe. The cosmos was not just expanding. It was expanding faster and faster, driven by something we could not see, could not touch, could barely comprehend. And that brings us to the question that has occupied physicists ever since. What is dark energy? What is this thing that makes up 68% of the universe and causes space itself to stretch? We do not know, but we have ideas. We have theories, and those theories are as strange and beautiful as the mystery itself. The leading candidate, the one that most closely matches Einstein's cosmological constant, is vacuum energy. The idea is that empty space is not actually empty. Even in the most perfect vacuum, the kind of vacuum you might create in a laboratory, by pumping out every last atom of gas, there is still something there. Quantum mechanics tells us that at the smallest scales, space is a seething foam of activity. Particles and antiparticles pop into existence and then annihilate each other almost instantly. These quantum fluctuations are not just a theoretical curiosity. They have measurable effects. The Casimir effect, for instance, demonstrates that the vacuum exerts a real, measurable pressure on objects placed very close together in empty space. Vacuum energy is the idea that these quantum fluctuations carry energy, and that this energy is associated with a pressure that is negative, meaning it causes space to expand rather than contract. The more space there is, the more vacuum energy there is. And because vacuum energy is a property of space itself, it does not dilute as the universe expands. Ordinary matter becomes less dense as the universe grows, because the same amount of matter is spread over a larger volume, but vacuum energy stays constant per unit volume, which means the total amount of vacuum energy actually increases as the universe expands. This creates a feedback loop. More space means more vacuum energy, which means more expansion, which means more space, and so on. This is why the expansion accelerates. There is a problem with this idea, though, a big one, when physicists try to calculate how much vacuum energy there should be. Based on our understanding of quantum mechanics, the result is absurdly large. The predicted value is somewhere around 10 to the power of 120 times larger than what we actually observe. That is not a small discrepancy. That is the largest mismatch between theory and observation in the entire history of science. It is as if you tried to predict the weight of a feather, and your calculation came out with the mass of the entire observable universe. This is known as the cosmological constant problem, and it remains one of the deepest unsolved puzzles in theoretical physics. Some physicists argue that this discrepancy means we are missing something fundamental about how quantum mechanics and gravity interact. Others suggest that there may be some cancellation mechanism we do not yet understand, some symmetry or principle that reduces the vacuum energy to the tiny value we observe. And still others think that vacuum energy, despite its problems, is still the best explanation we have, and that the discrepancy will eventually be resolved by a more complete theory of quantum gravity. But vacuum energy is not the only option. There is another idea, one that is perhaps even stranger. It is called quintessence. The name comes from ancient philosophy, where it referred to a fifth element beyond earth, air, fire, and water. In modern cosmology, quintessence is a dynamic form of dark energy, a field that permeates space and changes over time. Unlike the cosmological constant, which is fixed and unchanging, quintessence can evolve. Its energy density can increase or decrease as the universe ages. its pressure can vary. It can be stronger in some regions of space and weaker in others. Think of quintessence as a kind of fluid that fills the universe, but a fluid with very unusual properties. Instead of behaving like water or air, it behaves in a way that creates negative pressure, pushing space outward. And unlike vacuum energy, which is constant, quintessence can change. It might have been negligible in the early universe and only become dominant more recently, which would explain why the acceleration of the expansion is something we are only now detecting. It might continue to evolve in the future, growing stronger or weaker, shaping the fate of the cosmos in ways we cannot yet predict. The quintessence model is appealing to some physicists because it offers a way to address the cosmological constant problem. If dark energy is not a constant, but a dynamic field, then its current value is not a fixed number that needs to be predicted from first principles. It is simply the value the field has right now, at this particular moment in cosmic history. It was different in the past and will be different in the future. This makes the coincidence of why dark energy is becoming dominant just now, at roughly the present epoch, somewhat less puzzling. Although it introduces its own set of questions about the nature of the field and its evolution, there are many specific models of quintessence, each with different mathematical forms and different predictions. Some involve scalar fields similar to the Higgs field. Others involve more exotic constructions borrowed from string theory or other frameworks of theoretical physics. None of them have been confirmed by observation, but none of them have been ruled out either. The data we have so far is consistent with both a cosmological constant and with various forms of quintessence, and distinguishing between them requires measurements that are even more precise than what we can currently achieve. Then there is a third possibility, one that takes an entirely different approach. What if dark energy is not a thing at all? What if it is not a form of energy or a field or a property of the vacuum, but rather a sign that our understanding of gravity is incomplete? This is the modified gravity approach. The idea is that general relativity, Einstein's theory of gravity, works beautifully on the scale of the solar system and even on the scale of galaxies, but that it may need to be adjusted on the largest scales, the scales of the entire universe. Modified gravity theories propose that the laws of gravity change slightly at very large distances or very low accelerations. On the scale of a solar system, gravity behaves exactly as Einstein predicted. On the scale of a galaxy, it also behaves as expected, although dark matter is usually invoked to explain the extra gravitational pull. But on the scale of the entire cosmos, the rules might be different. The expansion of the universe might not require a mysterious form of energy to accelerate it. Instead, the acceleration might be a natural consequence of gravity behaving differently on the largest scales. One of the most famous modified gravity theories is called MOND, or modified Newtonian dynamics, proposed by Mordechai Milgram in the 1980s. MOND was originally designed to explain galaxy rotation curves without invoking dark matter, and it has had some success in that regard. But extending modified gravity to explain cosmic acceleration is a more challenging task. Various theories have been proposed, including FR gravity, which modifies the way curvature is related to matter in Einstein's equations, and brane world scenarios, which suggest that our universe is a three-dimensional surface embedded in a higher dimensional space, and that gravity can leak into those extra dimensions in ways that affect the large-scale behavior of the cosmos. The modified gravity approach is attractive to some because it eliminates the need for dark energy altogether. If gravity itself is different on large scales, then there is no mysterious substance to explain. There is just a revised understanding of how gravity works. The challenge is that modified gravity theories must still be consistent with all the observations that confirm general relativity, from the bending of light around massive objects to the precise orbits of planets to the detection of gravitational waves. Any modification must be subtle enough to avoid contradicting these well-established results, while still being significant enough to explain cosmic acceleration. So, we have three broad categories of explanation for dark energy. Vacuum energy, the idea that empty space itself carries an energy that drives expansion. Quintessence, the idea that dark energy is a dynamic field that changes over time. And modified gravity, the idea that the acceleration is not caused by a new form of energy at all, but by a revision of our understanding of gravity on the largest scales. None of these have been confirmed. All of them remain active areas of research, and the truth may be something we have not even imagined yet. While the theorists debate and the observers measure, the universe continues to expand, and this expansion, this slow and patient drifting apart, has implications for the future of everything. The fate of the universe, the ultimate destiny of all matter and energy and space and time, depends on the nature of dark energy, and there are several possible endings, each one as strange and as quietly beautiful as the mystery that drives them. The most likely ending, the one that is consistent with dark energy behaving like a cosmological constant, is called the Big Freeze. It is also known as heat death, and it is the scenario in which the universe continues to expand forever, growing larger and colder and more dilute with every passing era. In this scenario, dark energy remains constant, a steady pressure that stretches space at an accelerating rate. Galaxies move further and further apart. The space between galaxy clusters grows so vast that eventually, from the perspective of any single galaxy, all other galaxies disappear beyond the observable horizon. The sky goes dark. This does not happen quickly. We are talking about timescales so long that they dwarf the entire history of the universe as we know it. The Milky Way and the Andromeda Galaxy are currently moving toward each other and will collide in about 4 billion years, forming a single larger galaxy. Stars will continue to form and die for trillions of years after that. But eventually, the supply of gas needed to form new stars will run out. The last stars will burn out. The universe will be filled with the remnants of dead stars, white dwarfs, neutron stars, and black holes, slowly cooling and fading. Over unimaginably long timescales, even these remnants will decay. Protons, the building blocks of atomic nuclei, may not be as stable as we think. If protons decay, as some theories predict, then all the matter in the universe will eventually dissolve into radiation and subatomic particles. Black holes, the most persistent structures in the cosmos, will slowly evaporate through a process called Hawking radiation, losing mass over trillions of years until they too disappear, and what remains is a universe filled with an incredibly thin soup of particles and radiation, spread so thinly across such an enormous volume of space that nothing interesting will ever happen again. The temperature will approach absolute zero. The universe will be in a state of maximum entropy, where no energy gradients exist to drive any process. This is the Big Freeze, a universe that does not end with a bang or a whimper, but with a slow, quiet fading into stillness. It sounds bleak, but I would encourage you to think about it differently. Think about it as the universe settling into a deep and permanent rest. All the drama, all the collisions and explosions and births and deaths, all the activity that has characterized the cosmos for nearly 14 billion years will eventually give way to a state of perfect equilibrium. The universe will not be destroyed. It will not be torn apart. It will simply become still. And there is something deeply peaceful about that. The universe, after all its tumult and turbulence, finally finds its quiet. But there is another possibility, one that is more dramatic and has captured the imagination of science writers and the public alike. It is called the Big Rip. In this scenario, dark energy does not remain constant. It grows stronger over time. The pressure that is causing the universe to expand accelerates not just the expansion, but the acceleration itself. The rate of expansion increases without bound, and eventually, the stretching of space becomes so violent that it tears apart every structure in the universe. This would not happen all at once. It would unfold in stages, each one marking the destruction of a different scale of structure. First, galaxy clusters would be pulled apart. The space between galaxies would grow so rapidly that the gravitational bonds holding clusters together would be overwhelmed. Then, individual galaxies would be torn apart. The space between stars would expand faster than gravity could hold them in orbit. Then solar systems would be disrupted. The space between planets and their stars would stretch until the planets drifted away, and finally, in the last moments, even atoms would be ripped apart. The space between atomic nuclei and their electrons would expand so rapidly that no force could hold them together. Matter itself would cease to exist. The Big Rip is a dramatic and terrifying scenario, and it has received a lot of attention for that reason. But I want to be clear about something. The Big Rip is not the most likely outcome. The data we have so far is most consistent with dark energy behaving like a cosmological constant, which leads to the Big Freeze, not the Big Rip. For the Big Rip to happen, dark energy would need to have a very specific property, one that physicists call a phantom equation of state. It would need to have a pressure that is even more negative than what a cosmological constant produces. There is no strong evidence for this. It is possible, but it is not the leading prediction. And even if the Big Rip were to happen, it would not happen for a very, very long time. The earliest estimates put the time until the Big Rip at around 22 billion years from now. That is more than 16 billion years from the present. By any human standard, that is effectively forever. The Earth will have been consumed by the expanding sun billions of years before the Big Rip could even begin to affect the structures of the universe on a meaningful scale. We are talking about an event so far in the future that it is almost abstract, but I think there is value in contemplating both scenarios, the Big Freeze and the Big Rip, not because we need to worry about them, but because they help us understand the nature of the universe we live in. They help us appreciate the delicate balance that allows galaxies and stars and planets and life to exist at all. If dark energy had been significantly stronger in the early universe, the expansion would have been so rapid that matter would never have had a chance to clump together and form structures. No galaxies, no stars, no planets, no us. The fact that dark energy is weak enough to allow structure to form, but strong enough to eventually dominate the expansion, is one of the many coincidences that make the universe the way it is. There is a strange irony in all of this, and I want to sit with it for a while, because it is the kind of irony that is best appreciated in a state of quiet contemplation, the kind you might find yourself in right now, as your body relaxes and your mind drifts. The irony is this: the majority of the universe is made of things we cannot see, cannot touch, cannot understand. 68% dark energy, 27% dark matter, 5% normal matter. 95% of the cosmos is invisible. We are surrounded by a vastness that is fundamentally unknowable, at least with our current tools and our current understanding. Think about what that means. Every scientific instrument ever built, every telescope, every particle detector, every spectrometer, every interferometer, all of them together can only detect 5% of what exists. The rest is hidden from us. We infer its presence through its effects. We see galaxies rotating too fast, and we conclude there must be extra mass we cannot see. We see the expansion accelerating, and we conclude there must be some form of energy we cannot detect. We are like people living in a house where 95% of the rooms are invisible. We can hear sounds coming from those rooms. We can feel drafts of air moving through the walls. We can measure the effects of whatever is happening in there, but we cannot see it. We cannot go inside. We can only guess. And yet, we keep guessing. We keep building better instruments, developing better theories, pushing the boundaries of what we can observe and understand. We are driven by a curiosity that is as fundamental as gravity, as persistent as dark energy itself. We want to know. We want to see the invisible rooms. We want to understand the 95%. And maybe someday we will. Maybe the next generation of telescopes, the next breakthrough in theoretical physics, the next unexpected observation will reveal something that changes everything. Maybe dark energy will turn out to be something we can describe with a simple equation, something elegant and obvious in hindsight. Maybe it will turn out to be something so strange that we need entirely new concepts to understand it. Or maybe we will never fully understand it. Maybe dark energy will remain a mystery, a permanent feature of the cosmic landscape that we can measure and model, but never truly comprehend. And there is something beautiful about that too. A universe that is fully understood is a universe that has lost its capacity to surprise. A universe that holds mysteries is a universe that remains alive, in a sense, full of questions that invite us to keep looking, keep wondering, keep reaching. You are breathing slowly now, and the rhythm of your breath is a kind of expansion and contraction of its own. Air flows in, filling your lungs, and then flows out, leaving space for the next breath. The universe does something similar in its own way. Space expands, creating more room, more distance, more emptiness between the things that exist. But that emptiness is not nothing. It is filled with dark energy, with the quantum foam of vacuum fluctuations, with the subtle pressure that is slowly, gently pushing everything apart. The emptiness is full. The void is alive with activity, just at a scale we cannot directly perceive. Let me take you through a thought experiment, something to picture as you rest. Imagine you are floating in space, far from any star or planet, in the deep void between galaxies. There is no up or down, no sense of direction, just an endless expanse of darkness in every direction. You cannot see the galaxies from here. They are too far away, too dim, reduced to faint smudges of light that would require a powerful telescope to resolve. All around you is darkness, and in that darkness, something is happening. Space itself is expanding. The distance between any 2 points is slowly increasing. not because the points are moving through space, but because the space between them is growing. If you were to place two markers in the void, a meter apart, and wait, you would eventually find that they are no longer a meter apart. The space between them has stretched. The markers have not moved. They have simply been carried apart by the expansion of the space they inhabit. This is what is happening everywhere in the universe, right now, at this very moment. The space between you and the nearest star is growing. The space between the Earth and the moon is growing. The space between the atoms in your body is growing. The effect is incredibly small on these scales, far too small to measure or notice, but it is there. On the largest scales, the effect accumulates, and over billions of years, it becomes the dominant force shaping the cosmos. And it is not violent. It is not a tearing or a ripping or a shattering. It is a stretching, a gentle and patient expansion that carries things apart the way a slow current carries boats on a lake. The galaxies are not being destroyed. They are not being torn apart. They are simply being carried away from each other by the growing space between them. The universe is not ending. It is changing. And change on these timescales is not something to fear. It is simply the way things are. Think about the patience of this process. The universe has been expanding for nearly 14 billion years. 14 billion. That is a number so large that the human mind cannot truly grasp it. If you were to count one number per second, it would take you 14 billion seconds to reach the age of the universe. That is about 444 years of non-stop counting. And during all of that time, the expansion has been going on, steady and relentless, shaping the cosmos in ways that are only now becoming clear. The acceleration of the expansion, the effect of dark energy, has only been dominant for the last few billion years. Before that, gravity was the dominant force on large scales, slowing the expansion, pulling matter together, forming galaxies and clusters. Dark energy was there, but it was not strong enough to overcome gravity. It was only as the universe grew and the density of matter decreased that dark energy became the dominant influence. A quiet takeover, a gradual shift in the balance of power from one cosmic force to another. There is a kind of poetry in that. Gravity, the force that brings things together, that creates structure and complexity and beauty, dominated the early universe. Dark energy, the force that pushes things apart, that stretches and dilutes and eventually stills, is taking over. It is not a conflict. It is not a battle. It is a transition, a natural progression from one phase of cosmic evolution to the next. The universe is not being destroyed. It is growing up. It is moving from a phase of construction to a phase of quiet expansion. And there is something deeply natural about that. Let us talk a little more about the teams that made the discovery in 1998, because their story is worth lingering on. The Supernova Cosmology Project and the Ia Supernova Search Team were in a sense competitors. Both were racing to measure the expansion rate of the universe using type Ia Supernovae. Both expected to find that the expansion was slowing down. That was the assumption built into their experimental design. They were looking for evidence of deceleration. They were not looking for acceleration, and when the data came in, when the distant supernovae turned out to be dimmer than expected, both teams had to confront the possibility that they were seeing something completely unexpected. There is a moment in science, a moment that every scientist hopes for and dreads in equal measure, when the data refuses to conform to expectations, when the numbers on the screen tell a story that contradicts everything you thought you knew. That moment is terrifying and exhilarating at the same time. It is terrifying because it means you might be wrong. It is exhilarating because it means you might be about to discover something new. The teams in 1998 found themselves in exactly that position. The data said the expansion was accelerating. Their initial reaction was skepticism. They checked their instruments, reanalyzed their data, looked for sources of error. Dust in the distant galaxies could make supernovae appear dimmer. Evolution in the properties of supernovae over cosmic time could affect their brightness. There were many possible explanations that did not require new physics, but the teams ruled those out one by one. The evidence kept pointing in the same direction. The expansion was accelerating. And when both teams, working independently with different data sets and different methods, arrived at the same conclusion, the result was as close to certain as science ever gets. The universe was not just expanding. It was expanding faster and faster. Adam Rees, one of the members of the High Z team, has described the moment when he first saw the result as a feeling of disbelief, followed by a feeling of awe. He knew that if the result was correct, it would change everything. And it did. The discovery of accelerating expansion is widely regarded as one of the most important findings in the history of cosmology, right up there with Hubble's discovery of the expanding universe and the detection of the cosmic microwave background radiation. It fundamentally altered our picture of the cosmos and opened up entirely new questions about the nature of space, time, and energy. And yet, for all its significance, the discovery was made by looking at exploding stars, by measuring the brightness of distant points of light, by comparing what those points of light looked like to what they should have looked like if the universe were slowing down. It was a simple measurement carried out with telescopes and cameras and computers, the same tools astronomers have used for centuries, just better. There is something deeply humbling about that. The greatest discoveries are often the simplest. You look at the sky, you measure what you see, and you let the data tell you the truth, even when the truth is not what you expected. The sky, by the way, is a good place to turn your attention right now, even if you cannot see it, even if you are indoors, even if it is daytime. even if you are in a city where the lights drown out the stars, the sky is still there, above you, vast and dark, and full of things you cannot see. The dark energy that fills the universe is in the room with you right now. It is in the space between the walls, between the objects on your bedside table, between the molecules of air you are breathing. It is everywhere, always, filling every gap, every void, every emptiness with its gentle, persistent pressure. You might find it strange to think about emptiness as something that has substance, that has energy, that has an effect on the world around you. But emptiness is never truly empty. Even in the deepest void between galaxies, there are quantum fluctuations, particles appearing and disappearing, fields oscillating at frequencies we cannot detect. The vacuum of space is a rich and complex place, and dark energy may be one of its most fundamental properties. It may be the price of existence, the cost of having space at all. Space wants to expand. It is in its nature to grow, to stretch, to create more of itself. And that tendency, that fundamental desire of space to be more than it is what we call dark energy. I want to talk for a moment about the word dark, because it is a word that carries a lot of baggage. In our everyday language, dark is associated with fear, with the unknown, with danger. We are afraid of the dark because we cannot see what is in it. We imagine threats lurking in the shadows. But in the context of cosmology, dark does not mean threatening. It means invisible. Dark matter is called dark because it does not emit or reflect light. Dark energy is called dark because we cannot see it directly. There is nothing sinister about either of them. They are simply things we cannot observe with our eyes or our conventional instruments. They are hidden from us, not because they are malevolent, but because they do not interact with light in the ways that ordinary matter does. In fact, if you think about it, most of what is important in life is invisible. Love is invisible. Gravity is invisible. The forces that hold atoms together are invisible. The electrical signals in your brain that give rise to your thoughts and memories and sense of self are invisible. The fact that the majority of the universe is invisible should not be surprising. It should be expected. The visible world is just the surface. Beneath it, and beyond it, and woven through it, there is a vast, invisible reality that gives the visible world its shape and its meaning. Dark energy is part of that invisible reality. It is the thing that gives the universe its trajectory, its direction, its ultimate fate. Without dark energy, the universe would be a very different place. It might have collapsed back on itself billions of years ago in a big crunch. It might have expanded forever, but at a constantly slowing rate, never accelerating, never reaching the state of dominance that dark energy now holds. The presence of dark energy, whatever it is what makes the universe the way it is, and the fact that we only discovered its existence in 1998, after centuries of looking at the sky and thinking we understood it. is a reminder of how much there is still to learn. Let me slow down even further, because the cadence of this story should match the cadence of your breathing, and your breathing should be slow now, slower than it was at the beginning, deeper and more relaxed. You are settling into whatever surface is beneath you, and that surface is supporting you, holding you up, doing its job without any effort on your part, just as the Earth holds you without effort, just as the galaxy holds the solar system without effort, just as the universe holds everything within it, expanding and stretching and carrying it all along in a slow, patient drift. The expansion of the universe is not something you can feel. The space between the atoms in your body is growing, but the effect is so small that it is completely overwhelmed by the forces that hold those atoms together. The electromagnetic force that binds electrons to nuclei is vastly stronger than the effect of dark energy on atomic scales. The strong nuclear force that holds atomic nuclei together is even stronger. Gravity, the weakest of the fundamental forces, is still far stronger than dark energy on the scale of a planet or a star. It is only on the largest scales, the scales of galaxy clusters and beyond, that dark energy becomes the dominant influence. This is why you can rest easy tonight. The expansion of the universe is not going to pull you apart. It is not going to affect anything in your immediate environment. The forces that hold you together, that hold the Earth together, that hold the solar system together, are far too strong for dark energy to overcome. You are safe. The universe can expand all it wants, and you will remain exactly as you are, held together by forces that are local and strong and reliable. But on the largest scales, the expansion continues, and the galaxies that are not gravitationally bound to our own local group are already moving away from us at speeds that increase with distance. The Andromeda Galaxy, our nearest large galactic neighbor, is actually moving toward us, and it will eventually merge with the Milky Way. This is because Andromeda and the Milky Way are gravitationally bound, part of the same local group, and on these smaller scales, gravity still wins, but beyond the local group, beyond the Virgo cluster, beyond any structure that is held together by its own gravity, everything is receding. Every galaxy, every cluster, every supercluster that is not bound to us by gravity is moving away, carried by the expansion of space, and the further away they are, the faster they are moving. This is Hubble's law, the relationship between distance and recession velocity that Edwin Hubble discovered in the 1920s. It is a simple, linear relationship. Double the distance, double the speed. And because of dark energy, that relationship is changing over time. The rate of expansion is increasing, which means that in the future, distant galaxies will be receding even faster than they are now. The Hubble constant, as it is called, is not really a constant. It changes over time, decreasing in the early universe as gravity slowed the expansion. And now increasing as dark energy takes over. There is a boundary in the universe beyond which we will never be able to see. It is called the cosmic event horizon, and it exists because the expansion of space is accelerating. Galaxies beyond a certain distance are receding from us faster than the speed of light. This does not violate relativity because the galaxies are not moving through space faster than light. The space between us and them is expanding, and that expansion can carry them away at any speed. Once a galaxy crosses the event horizon, its light can never reach us. It is gone from our observable universe, not because it has been destroyed, but because the space between us has grown so vast that no signal can cross it. This is already happening. There are galaxies that we can see now, whose light has been traveling toward us for billions of years, that will eventually cross the event horizon and disappear from view. Their light, the light we are seeing now, is the last light we will ever receive from them. After that, they will be gone, forever beyond our reach. The observable universe is shrinking, in a sense, not because galaxies are disappearing, but because the space between us is growing too fast for their light to keep up. This is not a violent process. It is not a sudden disappearance. It is a gradual fading, a slow dimming, as the light from distant galaxies becomes redder and dimmer and eventually vanishes entirely. It is the cosmic equivalent of watching a ship sail over the horizon. The ship does not disappear all at once. The hull goes first, then the deck, then the mast, and finally the tip of the mast, and then the ship is gone. The galaxies are doing the same thing, sinking below the cosmic horizon, one by one, over billions of years, and what will be left in the far, far future is just the local group. The Milky Way and Andromeda merged into a single galaxy, surrounded by a handful of smaller companion galaxies, all gravitationally bound together. Everything else will have drifted beyond the horizon, carried away by the expansion of space. The sky of the far future will be dark, filled only with the stars of our own merged galaxy. The cosmic microwave background radiation, the afterglow of the Big Bang, will have redshifted to such long wavelengths that it will be undetectable. Future astronomers, if there are any, will look out at the sky and see nothing but their own galaxy, surrounded by endless darkness. They will have no evidence of the Big Bang, no evidence of the expanding universe, no evidence of the billions of galaxies that once filled the cosmos. They will think that their galaxy is the entire universe. This is a strangely poignant thought. All of the evidence that we have gathered, all of the observations that have led us to our current understanding of the cosmos, will eventually become inaccessible. The universe will erase its own history, hiding the evidence of its origin and evolution behind an impenetrable horizon. Future civilizations will have to deduce the nature of the cosmos from the limited information available within their own galaxy. and they may never be able to reconstruct the full picture. It is as if the universe is slowly closing the book on its own story, chapter by chapter, until only the final chapter remains. But that is the far, far future. We are here now, in the present, in a universe that is still rich with observable evidence, still full of galaxies we can see and study, still brimming with the remnants of its history. We are living in a privileged time, a time when the universe is old enough to have formed complex structures, but young enough that the evidence of its origin is still visible. The cosmic microwave background radiation is still detectable. The galaxies are still close enough to observe. The supernovae are still bright enough to measure. We are living in the golden age of cosmology, and we should appreciate it. Let me take you back to the supernovae, because they are the thread that ties this whole story together. Type Ia Supernovae are not just standard candles. They are also clocks, because they explode with a known luminosity. Their light curves, the way their brightness changes over time, can be used to measure not just distance, but also the expansion rate of the universe at the time the light was emitted. By comparing supernovae at different distances, the teams in 1998 were able to reconstruct the expansion history of the universe, going back billions of years. What they found was a history with two distinct phases. In the first phase, the early universe, gravity dominated. The expansion was slowing down, pulled back by the mutual attraction of all the matter in the cosmos. Galaxies were forming, stars were being born, the universe was building its structures. This phase lasted for billions of years, long enough for the complexity we see today to emerge. Then, as the universe grew and the density of matter decreased, dark energy became dominant. The expansion began to accelerate. The universe entered its second phase, the phase of accelerated expansion, the phase we are in now. This transition from deceleration to acceleration happened roughly 5 to 6 billion years ago, around the time the solar system was forming. Think about that. The Earth, the Sun, the planets, the ingredients of life, all of it came together at roughly the same moment that the universe switched from slowing down to speeding up. It is a coincidence, probably, but a beautiful one. The conditions that allowed life to emerge on Earth were happening at the same time that the cosmos was entering a new phase of its evolution. We are, in a very real sense, children of the transition. The type Ia Supernovae that made this discovery possible are themselves fascinating objects. They are the death throes of white dwarf stars, the dense remnants of stars like our sun. A white dwarf is what is left after a sun-like star has burned through all of its nuclear fuel and shed its outer layers. What remains is a core of carbon and oxygen, compressed to an extraordinary density. A white dwarf is about the size of the Earth, but has the mass of the sun. A teaspoon of white dwarf material would weigh tons. When a white dwarf is part of a binary system, orbiting a companion star, it can pull material from that companion. This material accumulates on the surface of the white dwarf, and if enough of it accumulates, the white dwarf reaches a critical mass called the Chandrasekhar limit, named after the Indian astrophysicist Subramanian Chandrasekhar. At this point, the pressure and temperature at the center of the white dwarf become high enough to ignite a runaway thermonuclear reaction. The entire star explodes in a matter of seconds, releasing as much energy as the sun will release in its entire lifetime. The explosion is so bright that it can outshine an entire galaxy for a few weeks. And because the critical mass is always roughly the same, the brightness of the explosion is always roughly the same. This is what makes type Ia Supernovae such useful standard candles. They are cosmic lighthouses, flashing with a known intensity, allowing us to measure the distances to the galaxies in which they reside. The teams that discovered the accelerating expansion had to find these supernovae in distant galaxies, which is no easy task. Supernovae are rare events. A galaxy like the Milky Way might produce 1 or 2 type Ia supernovae per century. To find enough supernovae at different distances to measure the expansion history, the teams had to monitor thousands of galaxies, taking repeated images over months and years, searching for the brief flashes of light that signaled an explosion. It was painstaking work, requiring patience and precision, and a willingness to stare at thousands of images of the sky, looking for the one pixel that had changed. And they found them. They found dozens of supernovae at distances ranging from a few 100 million light years to several billion light years. And they measured their brightness and their redshifts, and they plotted the data, and they saw the curve that told them the universe was accelerating. It was a curve that no one expected, a curve that defied the assumptions built into the experimental design, a curve that said something fundamental about the nature of the cosmos was different from what anyone had imagined. The discovery was announced at a meeting of the American Astronomical Society in January 1998. The room was packed. The results were presented, and the reaction was a mixture of excitement and skepticism. This was a big claim, and big claims require big evidence. But the evidence was there, in the data, in the brightness of the distant supernovae, in the way they deviated from the predictions of a decelerating universe. And when the second team, working independently, announced essentially the same result a few weeks later, the skepticism began to melt away. 2 teams, 2 data sets, 2 methods, the same conclusion. The expansion was accelerating. Since then, the result has been confirmed by many independent lines of evidence. The cosmic microwave background radiation, the afterglow of the Big Bang, contains subtle patterns that are consistent with a universe dominated by dark energy. The large-scale structure of the universe, the distribution of galaxies and galaxy clusters across the sky, also points to the same conclusion. Baryon acoustic oscillations, the fossilized sound waves from the early universe, provide another independent measurement that agrees with the supernova results. All of these different methods, all of these different approaches point to the same picture. A universe that is 68% dark energy, 27% dark matter, and 5% normal matter. A universe that is expanding at an accelerating rate. A universe whose fate is to drift slowly, patiently, into a state of quiet stillness. The convergence of evidence is one of the most satisfying aspects of science, when different methods, based on different physical principles, all point to the same conclusion. You can be confident that the conclusion is real. It is not an artifact of one particular instrument or one particular analysis. It is a feature of the universe itself. And the convergence of evidence for dark energy is about as strong as it gets. Every independent test confirms the picture. The universe is dominated by something we cannot see, and that something is pushing everything apart. I want to spend some time with the composition of the cosmos, with those three numbers that define our universe. 68% dark energy, 27% dark matter, 5% normal matter. These numbers come from the Planck satellite, a space observatory operated by the European Space Agency that measured the cosmic microwave background radiation with unprecedented precision. The Planck data, combined with other observations, gives us the most accurate picture we have of the composition of the universe. And it is a picture that is as humbling as it is fascinating. Normal matter, the 5%, is everything we are familiar with. Protons, neutrons, electrons, the particles that make up atoms, the atoms that make up molecules, the molecules that make up everything you can see and touch and taste and smell. Stars, planets, gas, dust, living organisms. All of it is normal matter. And it is only 5%. 5%. The rest is something else. Dark matter, the 27%, is the invisible scaffolding. It is the thing that holds galaxies together. That provides the extra gravity needed to explain the rotation curves of galaxies and the motions of galaxy clusters. It is called dark because it does not interact with light. It does not emit, absorb, or reflect electromagnetic radiation of any kind. It is completely transparent, completely invisible. We can only detect it through its gravitational effects. It is like a ghost, present but unseen, shaping the visible world without revealing itself. Dark matter is not as mysterious as dark energy, in the sense that we have a better idea of what it might be. The leading candidate is a class of particles called WIMPs, weakly interacting massive particles. These are hypothetical particles that would interact with normal matter only through gravity and the weak nuclear force, making them extremely difficult to detect. Decades of experiments have searched for WIMPs, using detectors buried deep underground to shield them from cosmic rays. But so far, no definitive detection has been made. Other candidates include axions, sterile neutrinos, and various other exotic particles predicted by theories beyond the standard model of particle physics. Dark matter is also not as mysterious as dark energy in the sense that it clumps, it forms structures. It gathers in halos around galaxies, in filaments that connect galaxy clusters, in a vast cosmic web that spans the entire observable universe. Computer simulations of dark matter, based on our understanding of its gravitational behavior, produce structures that closely match what we observe in the real universe. This is one of the great successes of modern cosmology, the dark matter model. Despite the fact that we have not yet detected dark matter particles directly, makes predictions that are borne out by observation. The cosmic web, the distribution of galaxies, the gravitational lensing of distant objects by intervening mass. All of these are consistent with a universe dominated by dark matter on intermediate scales, but dark energy is different. Dark energy does not clump. It does not form structures. It is spread evenly throughout the universe, a uniform background pressure that affects everything equally. It is the smoothest thing in the cosmos, and that smoothness is part of what makes it so difficult to understand. We cannot study it by looking at its structure, because it has none. We can only study it by measuring its effect on the expansion of the universe, by observing how the distances between objects change over time. And the effect is subtle. The acceleration of the expansion is a tiny effect, noticeable only on the largest scales and over the longest times. On the scale of the solar system, the effect is completely negligible. On the scale of a galaxy, it is still negligible. It is only on the scale of the entire universe, the scale of billions of light years, that the effect becomes significant. This is why it took until 1998 to discover. The instruments had to be good enough. The observations had to be precise enough. The data had to be extensive enough to detect an effect that is so small and so gradual. And even now, we are still refining our measurements, the exact nature of dark energy, whether it is truly a cosmological constant or something more complex like quintessence, is still an open question. New telescopes and new surveys are being built to answer this question. The Vera C. Rubin Observatory in Chile, the Nancy Grace Roman Space Telescope, the Euclid mission from the European Space Agency. All of these are designed to measure the expansion history of the universe with unprecedented precision, to distinguish between different models of dark energy, to pin down the equation of state, the relationship between the pressure and energy density of dark energy. The equation of state is denoted by the letter W. And for a cosmological constant, W equals exactly -1. For quintessence, W can vary and can be different from -1. Current measurements suggest that W is very close to -1, consistent with a cosmological constant. But the uncertainties are still large enough that we cannot rule out more exotic possibilities. The next generation of observations will shrink those uncertainties and perhaps finally give us a clear answer. Or perhaps they will reveal something even stranger, something we have not yet imagined. Let us return to Einstein, because his story is not quite finished. The cosmological constant, the term he introduced and then discarded, has had a remarkable afterlife. After the discovery of accelerating expansion in 1998, the cosmological constant was resurrected, not as a fix to keep the universe static, but as the leading explanation for dark energy. The lambda-CDM model, the standard model of cosmology, includes the cosmological constant as a fundamental component. Lambda represents the cosmological constant, and CDM stands for cold dark matter. Together, they describe a universe that is dominated by dark energy and dark matter, with normal matter making up a small fraction. The lambda-CDM model is the most successful model of the universe ever devised. It explains the cosmic microwave background radiation, the large-scale structure of the universe, the abundance of light elements formed in the Big Bang, the accelerating expansion, and much more. It is a model that works, that makes predictions that are confirmed by observation, that provides a coherent framework for understanding the cosmos. And it is built on a foundation that includes Einstein's cosmological constant, the very term he called his biggest blunder. There is a kind of cosmic justice in this. Einstein was wrong about why the cosmological constant was needed, but he was right that it existed. The term he introduced to keep the universe static turned out to be the term that described the acceleration of the expansion. The blunder was not the term itself, but the reason for including it. And in the end, the universe vindicated the mathematics, even if it rejected the motivation. It is a reminder that in science, being right for the wrong reasons is still being wrong, and being wrong for the right reasons can still lead to something true. Einstein died in 1955, decades before the discovery of accelerating expansion. He never knew that his cosmological constant would be resurrected, that it would become a cornerstone of modern cosmology, that it would be recognized as one of the most important parameters in the history of physics. If he had known, I like to think he would have been amused. He was a man who valued elegance and simplicity in physical theories, and the cosmological constant is both elegant and simple. It is a single number, a single parameter that captures the essence of dark energy. The fact that this number has such profound implications for the fate of the universe is a testament to the power of simple ideas. The cosmological constant is not without its problems, as I mentioned earlier. The vacuum energy calculation that produces a value 120 orders of magnitude too large is a serious issue, one that has troubled physicists for decades, but the problems have not been enough to discard the idea entirely. The lambda CDM model still works, still makes accurate predictions, still provides the best fit to the observational data, and so the cosmological constant remains a mysterious but necessary component of our understanding of the cosmos. Some physicists are uncomfortable with this. They want a deeper explanation, a theory that predicts the value of the cosmological constant from first principles. That explains why it has the value it does rather than some other value, and they may be right to want that. Science is not satisfied with mere description. It wants understanding. It wants to know not just what is happening, but why. And the why of dark energy is still hidden from us, buried beneath layers of complexity that we have not yet unraveled. But there is also value in accepting what we do not know. There is value in saying, we do not understand this yet, and that is okay. The universe is under no obligation to be comprehensible to us. The fact that we have been able to understand as much as we have is remarkable, but it does not mean that we will understand everything. There may be aspects of the cosmos that are fundamentally beyond our reach, not because we are not smart enough or our instruments are not good enough, but because the universe is simply too vast and too complex for any single species to fully grasp, and that is fine. That is more than fine. It is beautiful. A universe that is fully understood is a universe that has been reduced to a set of equations. A universe that retains its mysteries is a universe that remains alive, that continues to surprise and inspire and challenge us. The mystery of dark energy is not a failure of science. It is an invitation to keep looking, keep measuring, keep theorizing, keep wondering. An invitation to participate in the oldest human endeavor, the attempt to understand the world around us, to make sense of the vastness, to find our place in the cosmos. You are still breathing slowly, and I hope you are feeling more relaxed now than when we started. The story of dark energy is not a stressful story. It is not a story about something threatening or dangerous or scary. It is a story about something gentle and patient and slow. Something that has been working in the background for billions of years, shaping the universe in ways that are only now becoming clear. It is a story about the quiet forces that govern the cosmos, the forces that do not shout or explode or demand attention, but simply persist, steadily and inevitably, carrying the universe along its path. The expansion of the universe is one of those quiet forces. It is not a violent tearing. It is a slow drifting, a patient separation, a gradual increase in the distance between things that were once closer together. It is the cosmic equivalent of two people who were once close slowly moving apart, not because of any conflict or disagreement, but simply because the ground beneath them is shifting, carrying them in different directions. There is no malice in it. There is no urgency. There is just the steady, inevitable progression of space expanding, creating more room, more distance, more emptiness between the islands of matter that dot the cosmos. And the islands themselves are not being destroyed. The galaxies are not being torn apart by the expansion. They are being carried along by it, each one a self-contained island of light and matter, held together by its own gravity, drifting through the growing void. The stars within the galaxies are not affected by the expansion on human timescales, or even on geological timescales. They live and die according to their own internal processes, burning their fuel, evolving through their various stages, and eventually fading away. The expansion of the universe is a background process, a slow rhythm that plays beneath the more immediate dramas of stellar birth and death. It is worth noting that the expansion of the universe does not mean that everything is getting bigger. The atoms in your body are not expanding. The Earth is not expanding. The solar system is not expanding. The Milky Way galaxy is not expanding. All of these structures are held together by forces that are far stronger than the effect of dark energy. The expansion only affects the space between structures that are not gravitationally bound. It is the space between galaxy clusters that is growing, not the space within the clusters themselves. The universe is not stretching like a piece of rubber. It is more like a loaf of raisin bread rising in the oven. The dough between the raisins is expanding, pushing the raisins further apart. But the raisins themselves are not getting bigger. This is a useful analogy, and one that astronomers have used for decades to explain the expansion of the universe. The raisins represent galaxies, and the dough represents space. As the dough rises, the raisins move further apart, but the raisins themselves do not change. From the perspective of any one raisin, all the other raisins appear to be moving away, and the further away a raisin is, the faster it appears to be moving. This is exactly what we observe in the universe. Every galaxy sees every other galaxy moving away, and the recession velocity is proportional to the distance. The raisin bread analogy also helps explain why the expansion does not have a center. When the dough rises, every raisin sees the same thing. Every raisin sees all the other raisins moving away, and no raisin is at the center of the expansion. The expansion is happening everywhere, simultaneously, in all directions. There is no point in the universe from which everything is expanding. The expansion is a property of space itself, not a movement of objects through space. This is one of the most counterintuitive aspects of cosmology, and it takes some time to internalize. We are used to thinking of motion as something that happens relative to a fixed background. A car moves along a road. A planet moves through space. But in an expanding universe, the background itself is changing. Space is not a fixed stage on which objects move. Space is a dynamic entity, one that can stretch and grow and change over time. expansion of the universe is not objects moving through space. It is space itself growing, carrying objects along with it. And space has been growing for nearly 14 billion years. From the moment of the Big Bang, when the universe was incredibly hot and dense, to the present day, when the universe is cool and dilute, space has been expanding, creating more room, more distance, more separation between the things that exist. The universe was once small enough to fit inside a single point, and now it is vast beyond comprehension, stretching for billions of light years in every direction, and it is still growing. The expansion has not stopped. It has not slowed. It has accelerated. The acceleration is the key insight, the discovery that changed everything. Before 1998, we thought the expansion was slowing down. We thought gravity was winning, gradually pulling back on the expansion, reducing the rate at which space was growing. And for the first several billion years, that was true. Gravity did slow the expansion. It took billions of years for dark energy to become dominant, for the density of matter to drop low enough that the constant pressure of dark energy could take over. But once it did, the expansion began to accelerate, and it has been accelerating ever since. This acceleration is what gives the universe its ultimate fate. If dark energy is a cosmological constant, constant in time and uniform in space, then the acceleration will continue forever. The expansion will never stop. The universe will grow larger and larger, colder and colder, more and more dilute, until it reaches the state of maximum entropy, known as the Big Freeze. If dark energy is something more complex, like quintessence, then the acceleration might change over time, might increase or decrease, might lead to a different fate. But the data so far points to a cosmological constant, and the cosmological constant points to the Big Freeze. The Big Freeze is not a dramatic ending. It is not an explosion or a collapse or a sudden event. It is a slow fading, a gradual dimming, a process that takes trillions upon trillions of years. It is the universe settling into a state of equilibrium, where nothing interesting happens anymore, where all the energy gradients have been smoothed out, where the temperature is the same everywhere, where no work can be done, no processes can occur, no changes can happen. It is the end of time, in a sense, not because time stops, but because nothing happens to mark its passage. But that is the very, very far future. We have trillions of years before the Big Freeze becomes even a remote concern. The sun will die in about 5 billion years, long before the last stars burn out. The Earth will be gone, consumed by the expanding sun, or torn apart by gravitational interactions, long before the galaxies drift beyond the horizon. We are living in the early stages of the universe's life, in a time when stars are still forming, when galaxies are still colliding, when the cosmos is still vibrant and active. The Big Freeze is not something to worry about. It is something to contemplate, a distant and abstract endpoint that helps us understand the nature of the universe we live in. And contemplation is what tonight is about. It is about lying down, closing your eyes, and thinking about the vastness of the cosmos, about the mysterious forces that shape it, about the fact that the majority of the universe is invisible and unknowable, and about the beautiful irony that the things we can see and touch and understand are just a tiny fraction of what is out there. It is about accepting that mystery is a permanent feature of existence, that there will always be things we do not understand, and that this is not a failure, but a gift. A universe without mystery would be a universe without wonder, and wonder is one of the most precious things we have. Dark energy is a mystery. We do not know what it is. We do not know why it has the value it does. We do not know whether it is truly a cosmological constant or something more complex. We do not know whether it will remain constant or change over time. We do not know whether it will lead to a big freeze or a big rip or something else entirely. All we know is that it is there, filling the universe with its gentle, persistent pressure, slowly, patiently, carrying everything apart. And that is enough for tonight. That is enough to think about as you rest, as you drift, as you let the weight of the day fall away from you. The universe is expanding. Dark energy is pushing. Galaxies are drifting apart. And you are here, safe and still, breathing slowly, held by forces that are local and strong and reliable. The expansion will not affect you. It will not pull you apart. It will not disrupt the structures that hold you together. You are anchored by gravity, by electromagnetism, by the strong and weak nuclear forces, all of which are far stronger than the effect of dark energy on any scale that matters to you. So you can let go. You can release whatever tension you are holding, whatever thoughts are circling in your mind, whatever worries are keeping you awake. The universe is taking care of itself. It has been for nearly 14 billion years, and it will continue to do so for trillions more. You do not need to hold it together. You do not need to keep it from falling apart. You can rest. You can close your eyes and drift, just as the galaxies are drifting, just as the universe is expanding, just as space itself is growing, slowly and patiently, creating more room for everything that exists. The cosmos is vast. It is mostly invisible. It is mostly mysterious. And it is beautiful, not because it is easy to understand, but because it is not. Not because it reveals all its secrets, but because it keeps some of them hidden. Not because it is static and unchanging, but because it is dynamic and evolving, always in motion, always expanding, always carrying everything along in its slow, patient drift. You have reached the end of the story, or at least the end of the part I have to tell. The rest of the story is still being written by astronomers who are building new telescopes, by physicists who are developing new theories, by curious minds who are asking questions that have never been asked before. The story of dark energy is not finished. It is still unfolding, and you are a part of it, just by being here, just by wondering, just by being alive in a universe that is mostly mystery. So close your eyes now, if they are not already closed. Feel the surface beneath you supporting you. Feel the air moving in and out of your lungs. Feel the stillness of the room, the quiet of the night, the vastness of the cosmos stretching out above you and around you and through you. The universe is expanding. Dark energy is pushing, and you are resting, safe and still, carried along by forces you cannot see, but can trust, just as the galaxies are carried along by the expansion of space. The story of the universe is a story of slow, patient change, of things drifting apart and coming together, of structures forming and dissolving, of light appearing and fading, of mysteries deepening, and occasionally, briefly, yielding to understanding. It is a story that has been going on for nearly 14 billion years, and it will continue for trillions more, and you are a part of it, a small but significant part, a conscious witness to the vastness, a mind capable of wondering about the invisible, a heart capable of being moved by the mystery. Sleep now. Let the story wash over you like a gentle tide, carrying you toward rest. The universe will keep expanding while you sleep. Dark energy will keep pushing. The galaxies will keep drifting, and you will keep breathing, slow and steady, held by the forces that bind you, carried by the earth that supports you, surrounded by the vastness that inspires you. You are part of something enormous and beautiful and mostly unknowable, and that is exactly as it should be. Good night, sweet dreams.